This movie is about naming ionic compounds from the formula. Before you can name any compound, you have to figure out what kind of compound it is. So let's make sure you do in fact have an ionic compound. So an ionic compound is typically going to have a metal or a polyatomic ion in it. So we're looking for a metal, something on the left side of the stair steps line on the periodic table, or we're looking for a polyatomic ion. Um, the polyatomic ions you have to look up on the polyatomic ion chart. Mainly, if you have a metal, if you don't have a metal, the only positive polyatomic ion that you're going to be seeing is ammonium, the NH4. So usually that's all we look for. If you have NH4 in your compound or a metal, then it's ionic. Okay. If it doesn't have a metal or NH4 and it's all covalent, or, or my bad, all nonmetals. Ooh. Then it's going to be covalent. It's a covalent compound, and there's a different set of rules for naming covalent compounds. If it begins with a hydrogen, okay, then it's going to be an acid, like HCl, things like that. All right? Okay, so if it is an ionic compound, there are basically three types of ionic compounds we can have. We can have what's called a binary ionic compound. It's basically a metal and a nonmetal. Okay, a metal ion and a nonmetal ion sticking to each other. An ionic compound with a transition metal has some different kind of rules. We use Roman numerals with that one to show the charge on the ion. Okay, and then we have polyatomic ions where we have to use the polyatomic ion chart or memorize the polyatomic ions. So let's look at some different kinds. So naming binary ionic compounds. So real simple ionic compounds with a metal and a non-metal. You basically write the name of the ions and you put them together. So for example, this one would be, we have the sodium ion. So that's going to be sodium. And then Cl would be the chloride ion. So that would be sodium chloride. The main thing you have to worry about with these compounds is make sure you write the positive ion first. The metal goes first, and then the nonmetal. And these nonmetal monatomic ions, the ones that are negative, we change their name so they end in IDE. So N with the 3 minus charge becomes the nitride ion instead of nitrogen. And phosphorus becomes the phosphide ion. And then we have the oxide ion, the sulfide ion, chloride, bromide, fluoride, and iodide. So if we look at this example right here, SRO, SR is going to be the strontium ion, so we write strontium. And O is the oxide ion, so we write oxide. And then this one, Mg, we looked that one up on the periodic table. It's magnesium. And F, that's fluorine, but remember we change it so that it ends in IDE, so it becomes the fluoride ion. So the name of this compound is magnesium fluoride. Here's some other examples: sodium fluoride, aluminum oxide, magnesium chloride, lithium phosphide, potassium iodide. You'll notice that no matter what the subscripts are, we don't add anything, any prefixes, okay? So like this is not a dialuminum trioxide. We don't do that with ionic compounds. We only do the prefixes with covalent compounds. So what if our ionic compound has a transition metal in it? Remember, the transition metals are in groups 3 through 12. And we do the same exact thing as we do with the other ionic compounds, with the exception is that we sometimes are going to use a Roman numeral that's going to stand for the charge of the metal ion, because these transition metals form more than one ion. They form more than one oxidation state. Like iron sometimes can be a +2 charge or a +3 charge. We have to have a way to show the difference between iron oxide with a +3 charge and iron oxide with a +2 charge. So we use Roman numerals to show for writing the name of the ion. So copper with a +1 charge is copper 1 ion, copper with a +2 charge is a copper 2 ion, and so on and so forth. Now there are some transition metals that only form one charge and they don't use Roman numerals. For example, silver, zinc, cadmium, and bismuth. Those are your most common ones that you're going to see. So we don't use Roman numerals with those, and so you just have to memorize that list. Okay. Here are some other transition metals that are named for you. Titanium 2 ion, the silver ion. Remember that's on the list. It doesn't form more than one thing, so it doesn't have a Roman numeral. Manganese 4 ion, zinc ion, that one's also on the list, and then nickel 3 ion. And here's some couple more examples. So if we have the compound formula, how do we know what the charge of the metal is? Well, the key thing here is that we may not know what the charge of the metal is, but we know two things. We know that the overall charge of the compound has to be 0, and that's true for all compounds. And then we know that the positive charge, that's going to be the charge on the copper, is going to be equal to but opposite of the negative charge. Okay? So basically we know the total positive charge, whatever it is on the positive side on the metals, okay, has to be equal but opposite to whatever the negative charge is. So I can figure out the charge on a fluoride. I just have to look on the periodic table. We go to the periodic table, we remember that the oxidation states are +1 for group 1, +2 for group 2. The transition metals use the Roman numerals, then +3 for group 13, +4 for the group 14 metals, and -4 for the nonmetals, -3 for group 15, -2 for group 16, and -1 for group 17, and of course 0 for group 18. So fluorine is in group 17, so it has a -1 charge. And so I know that each fluoride is going to bring a -1 charge. So I'm going to put the individual charge on the bottom. And since there's two of them, I'm going to multiply it by 2. That gives me a total of a -2 charge. Okay? So the total charge for both of those fluorides, for both of those right there, is -2. So that means the total charge over here has to be +2. Okay? Now since there's only one copper, that means that one copper has to be +2. And so this is going to be copper with a +2 charge, so it's a copper 2 ion, so copper 2 fluoride. We look at another, here's a procedure. If you need a procedure, you can just pause and just read through that. That just walks you through what we just talked about. Here's some more examples. If we have FeO, if I back up, oxygen's in group 16, it's right there. It has a -2 charge. Okay? So, oops, wrong way. So I know that that's going to be -2. The total is going to be -2. So the total on this side has to be +2. And so the individual here has to be +2 as well. So this is going to be iron 2 oxide. The next one, let me change the color so you can see it a little better. We know oxygen's a -2. We have 2 of those, so that's -4. So the total negative charge is -4, so the total positive charge has to be +4. So I'm putting the total charge on top and the individual charge on the bottom. So since there's one titanium, so it's +4 divided by 1. So the charge on the individual titanium is going to be a +4. So this is titanium 4 oxide. It's a Roman numeral 4, IV. Okay. Here we have a copper and we have a phosphate. A phosphate is a polyatomic ion, which we're going to talk about next. So we would have to look that one up on the periodic or on the polyatomic ion chart. The individual charge on a phosphate is a -3. There's 2 of them, so that gives us a -6. So that means the total positive charge must be +6. There's 3 of them, so 6 divided by 3 is a +2. So each copper is going to be a +2, so that's copper 2 phosphate. Ionic compounds are really easy to name. You just name the ions and put the ion names together. So copper 2 phosphate. This one's similar. We got an iron, Fe is iron, and SO4 is another polyatomic ion. That's the sulfate ion. So if we look at that one up on the polyatomic ion chart, it has a -2 charge. There's 3 of them, so 3 times -2 is -6. So that means the total positive charge has to be +6. Divided by 2, that means each individual Fe must be a +3. So this is iron, three sulfate. Um, Here's some more. We'll do, let's see. We'll do this. Do that one right there. This one, trick question. Zinc is on the list of those transition metals that don't use Roman numerals because they only form one charge. So this one's real easy. It is just zinc fluoride. Okay. Here we have copper and we have chlorine. We look on we look on the periodic table. Copper or chlorine is in group 17, so it has a -1 charge. So wrong way. So chlorine is -1. So copper must be a +1. Okay, so that's copper 1 chloride. All right, so ionic compounds with polyatomic ions. There are basically 3 kinds. You really don't need to know the kinds, but you can have a metal and a polyatomic ion. You can have a polyatomic ion and a nonmetal, and really the only positive polyatomic ion is going to be NH4. Or you can have a polyatomic ion and a polyatomic ion. So we're going to look at the 3 types. Now, how do you know if you have a polyatomic ion in your compound? Well, if you have a compound and it has more than 2 elements in it, in that compound, more than likely you have a polyatomic ion. Start looking on the chart to see if you can find it. Okay, the only time you're going to have only 2 elements and still have a polyatomic ion is when you have that peroxide. Okay, so like Na2O2. Okay, that's going to be sodium peroxide. Now the way that you tell that you have sodium peroxide, not sodium oxide, is look at the 2 and the 2. Okay, if this was, a normal ionic compound, that would reduce down. Okay, and sodium oxide, remember, is going to be Na2O because oxygen has a -2 charge and sodium has a +1 charge. And so we need 2 of those sodiums to cancel out that -2. So the only time you're going to see peroxide is in things like this and something in group 1 like Na2O2, H2O2, okay, hydrogen peroxide, or like K2O2, potassium hydroxide. Most of the other, those are pretty much the most common peroxides that you might see. Here's an example of an ionic compound with a metal and a polyatomic. You'll notice it has 1, 2, 3 different elements in it. That kind of tips us off that it has a polyatomic ion. Again, all we do is we name the ions. So Ca is the calcium ion. Okay, and then we have OH, and we have to look that one up, and we just go through the list, and here is OH right there. That is the hydroxide ion. Now notice it has an OH minus, right? Well, that minus, remember, is canceled out by that calcium. That's why we have to have 2 of those OHs. So this is calcium hydroxide. Look at the next one. we have another metal and a polyatomic. And again, if you're not sure what kind you have, you can just go to the polyatomic ion chart and start looking for whatever polyatomic ion might be on there. In this case, we have an SO4 right there, and so we know that SO4 is our polyatomic right there. And so Al is aluminum, so aluminum. And an SO4 we looked up was sulfate. And then here's a polyatomic and a nonmetal. So we have NH4, which is really the only positive polyatomic. Okay, so we find NH4 right here, and that is ammonium. So I'm going to write ammonium. And Cl is chlorine, but it's in an ionic form, so it's an ion, and so I name it chloride because I changed the ending so it ends in IDE. So ammonium chloride. Here we have a polyatomic and a polyatomic. Again, we have the NH4, so that's ammonium. And then we look on the periodic table for that SO4. Okay, there's the SO4. And so that's sulfate. And so it's ammonium sulfate. Okay, again, if we look, if we count the number of elements, I got one there, one there, one there. I got 4 different elements in this compound. So it tells me that more than likely I got a polyatomic ion. Okay? And that's basically how you write the formula for an ionic compound from the name. Oh, my bad. This is how you name an ionic compound from the formula.